Hi there everyone, I'm Songyuan from the Realm Lab at MIT. Today I'll introduce our work on how to solve the multi-agent safe optimal control problem with the distributed epigraph form multi-agent reinforcement learning. To begin with, let's imagine the future autonomous multi-agent systems. These systems all require robots to finish some team tasks collaboratively while maintaining safety at the same time. However, in reality, we have seen many news about accidents of these systems. Therefore, the problem we want to address is how to make autonomous multi-agent systems intelligent and safe. Going back to these systems, the problem can be formulated as a safe multi-agent optimal control problem, where we want to find distributed policies for each agent, which minimizes a team objective function, subjecting to constraints including safety, following unknown system dynamics. Mathematically, let L be the cost function of the team, H indicates the safe region, and let F be the dynamics function. The problem can be written in this way. Here we assume that the environment is partially observable. The problem can be solved by several approaches. One popular approach is the Lagrangian method, which results in a min-max problem. However, in practice, the Lagrangian method can cause unstable training. One of the fundamental reasons is that the gradients of the objective function scales linearly with lambda, and the large lambda can cause very large gradient steps. So, is there another way to solve this problem? The answer is yes, and we can use the epigraph form. We can show that the original problem is equivalent to this problem, with z being an auxiliary variable. The problem can be further written in this way. Here, z can be interpreted as a cost budget, which creates a sliding bar between performance and safety. With a small z, we have a low cost budget and have to focus on minimizing the cost. Therefore, we will learn an aggressive policy. With a large z, we can have a large cost, so the policy focuses on safety and has conservative behavior. With the optimal z, the policy achieves the best performance while maintaining safety. Comparing the epigraph form with the Lagrangian method, we can observe that using epigraph form, the gradient of the objective remains constant with different z, and therefore cannot explode. However, until now, everything is centralized. To make the policy distributed, we need to first define the centralized cost value function VL and the distributed constraint value function VH. Then the problem can be written in this way, and we can further define the total value function V. Then we develop a centralized training framework, where given a z, we learn the joint policy pi to minimize the total value function V. This can be done using standard multi-agent RL. At each iteration, we randomly sample a cost budget z and calculate the total value function, and use the PPO laws to update the policies. Then, during execution, we propose a theorem that under certain conditions, the centralized problem can be solved in the distributed manner, where each agent solves its own problem and get zi, then the connected agents calculate the maximum z among them to reach a consensus. Moreover, we observe that this z commutation part can be removed in practice, and we still have similar results. And this theorem allowed us to design a distributed execution part where each agent solves its own problem online and it gets own z for their z condition policies. The algorithm is tested on 8 different simulation environments, including the multi-agent particle environment and the safe multi-agent module environment. We compare our algorithm distributed epigraph form MARL or Def-MARL with the penalty method and the Lagrangian method with different parameters. Here we plot the cost as x-axis and the safety rate as the y-axis. In all environments, Def-MARL reaches the top left corner, which indicates that it achieves the best performance. We also did 2 hardware experiments. In the first environment, the crazy fly drone needs to fly through a corridor and reach their goals on the other side. In the second hardware experiment, the 2 crazy flies need to collaboratively inspect a moving target and keep the target being inside the observation range of at least 1 crazy fly. Using Def-MARL, one agent approaches and observes the target in the beginning, and when the goal is blocked, the other agent comes to help, so the target is always observed. Finally, here are the conclusions and the QR code for the website. Thank you.